Trigonometry and circles. When we're working with trigonometry and circles, we'll find that some basic propositions will help us to understand the rules that govern circles. Two of these are listed on the board, and they're very, very important propositions in concerning circles. If you look at the center of the circle and you draw a radius to the edge of the circle, you'll find that the line that's tangent at that very point where the radius intersects the circle is perpendicular. We're going to have the line of tangency perpendicular to the radius. You can see it makes a 90-degree angle. And in fact, it makes a 90-degree angle on each side. No matter where I draw the radius, if I draw the radius from the center down to the lower right-hand portion of the circle, I can draw a line of tangency there that will be perpendicular to the radius as well. Wherever you have a radius, if it intersects a tangent line at its point of tangency, you'll have right angles. In the second proposition, you have two lines of tangency drawn from the same point, drawn from P. We have a line that's tangent to the circle on the right side at B and a line that's tangent to the left side of the circle at A. If we draw a radius from C to B or from C to A, of course we know that we'll have two right angles. We have the two right angles here created by connecting a radius with a line of tangency at its point of tangency. We guarantee that in proposition 1. What we also find out is that when you draw a line segment connecting the point P with the center of the circle C, it will do the following things. It divides this angle, or bisects this angle at P, into two equal parts. So angle 1 and angle 4 are equal. We also know angle 3 and angle 5 are equal, and we can deduce that angle 2 and angle 6 are equal as well. Additionally, we have the tangent segments being equal. A tangent segment goes from the point outside the circle to the point of tangency. So PA, the tangent segment on the left, is equal to PB, the tangent segment on the right. Additionally, we have the radii being equal. CA is equal to CB because all radii in the same circle are equal, and CP is a line common to both triangles. So when we draw these lines of tangency from a point outside the circle and we connect that point to the center of the circle, we create two triangles in which each pair of corresponding angles is equal and each pair of corresponding sides is equal. In that case, we've created two equal or congruent triangles. In our first example, we have a drawing of two holes in a rectangle, and our challenge is to find the outer distance of the holes. I want to go from the outer edge of the top hole to the outer edge of the bottom hole. The drawing gives me some dimensions. It tells me that the distance from the center of the top hole to the center of the bottom hole is 1.250. The horizontal distance from the center of the top hole to the center of the bottom hole is 3.562. Given those measurements, I could easily find the distance from the center of one hole to the center of another hole using the Pythagorean theorem, and we'll use that as our starting point. We see that the leg of this triangle is 1.250 and the leg of this triangle is 3.562. That will enable us to find the distance of the hypotenuse connecting the center of the top hole to the center of the bottom hole. So we'll take 1.250, the leg, and square it. And we'll take the second leg, 3.562, and square it. And that will give us the length of the hypotenuse squared. And let's remember that the hypotenuse goes from the center of the top hole to the center of the bottom hole. So I'm going to move to my calculator to do this problem. I'm going to take 1.250 and square it. And I'm going to add that to 3.562, which I'm also going to square. And I'll find the total. Now this total is going to give me c squared, and I only want to find c, so I know that I have to take the square root of both sides of this equation. When I take the square root of c squared, I'll get the square root of this sum. Moving to my calculator, I'm trying to make this as simple as possible and let the calculator do the work. I've got my total in there, so I'll hit second square root, and I get 3.77496, which will round off to 3.7750. So I found that C is 3.7750, and I know that's the distance between the center of the top hole and the center of the bottom hole. Now that's not what we asked for in this problem, however. What we asked for was the distance from the outer edge to the outer edge. I know that I have to find the distance from the center to the outer edge in the top hole and the distance from the center to the outer edge in the bottom hole, and then add those distances in. I know that I have a 0.750 diameter according to this schematic. If I have a 0.750 diameter, I know the radius is equal to half of that, so 0.750 divided by 2. The radius of the top circle then is 0.375. On the other hand, in the bottom hole, I know I have a 0.500 diameter, and I need to divide that in half for the radius of that circle. So I'll have the radius is 0.500 divided by 2, or 0.250. Now, if I consider everything I have in this problem, I know that I have a distance from the center hole to the center hole of 3.7750. So I'll have 3.7750. In the upper circle, I know I have a distance from the center to the outer edge of 0.375. So I need to add 0.375. And I need to add the distance from the center of the bottom hole to the outer edge, which is 0.250. So I'll plus 0.250. I'll let my calculator do the work on this sum, and I'll have 3.7750 plus 0.375 plus 0.250. So the distance is 4.4. I'd like to remind you what that is. That is the distance from the outer edge of the top hole to the outer edge of the second hole. That's equal to the distance of x. We found x to be 4.4. Using our skills of the Pythagorean theorem and then using some common sense about circles, we were able to find out that answer. In our second example, we're trying to figure out what size pin will fit inside an equilateral triangle with sides equal to 0.194. In other words, we want to know the diameter of the circular pin that will fit snugly inside this equilateral triangle. Now we're going to use two of our propositions and some facts about right triangles to help us solve this particular problem. What I really want to know is the diameter of this circle. So I'm going to go ahead and draw in a radius of the circle. If I know the radius, I'll be able to find the diameter by doubling. I'm going to draw the radius so that it goes to the tangent line. The reason I'm doing that is because I know I can create right angles if I do so. So I've drawn in one radius in my triangle, in my circle. And I want to know this radius so that I can double it and find the diameter of the circle. Now the second thing I want to do is realize that I have a point of tangency. We'll call this point P. And I know lots of things about a point of tangency. I have two tangent lines drawn to the circle from point P. I know that if I connect point P to the center, the line will bisect this angle. Now another thing I know is since this is an equilateral triangle, each one of these angles must be 60 degrees, since all of the angles in an equilateral triangle are equal as well as the sides. So I'm going to connect P to the center of the circle, and I will create an angle bisector. We know that this angle has to be 60 degrees because this is an equilateral triangle and each angle is 60 degrees. We know the angles are equal in addition to the sides being equal. Now we've connected P to the center of the circle, so we know we've drawn in an angle bisector. That means we know that the angle at P has to be 30 degrees. We can start to see our triangle take shape here. We know an angle in the triangle and we know it's a right triangle because the radius and the tangent line will always make a right angle. Now the other thing I need to find is one side. I need to find one side. I know that the side of the equilateral triangle, the whole thing, is 0.194. And I know that the point of tangency to point P is half of that. So I have 0.194 divided by 2, which is 0.097. So I know the distance from the point of tangency to P is 0.097. Now I have everything I need to go ahead and find the missing side. And I'm going to let the missing side be x. If I'm looking for x, I'm going to think about the angle that I know, the 30 degrees, and I'm going to think, well, I don't know anything about the hypotenuse and I don't want to know anything about the hypotenuse. What I do want to know about is the side opposite the 30-degree angle, and I know something about the side adjacent to the 30-degree angle. So I know that in order to find x, I'm going to use the tangent ratio. I'm going to say the tangent of 30 degrees is equal to the ratio of the side opposite, x, over the side adjacent, 0.097. And I know that to solve this problem, I'm just going to cross multiply, so I'll have 0.097 times the tangent of 30 is equal to x. So I'm going to move to my calculator and do this calculation. I'll make sure that the calculator is cleared out, and I'll put in 0.097 times the tangent of 30. So I'll put in 30 tangent and hit enter. and I get 0.05600. So x is equal to 0.056. Now let's remember what x gives us. X only gives us the radius of this particular problem. What we're interested in is the diameter of the circle, but this is an easy enough problem to fix. If I want to know the diameter of the circle, I know that it's equal to 2 times the radius, and in this case I know what the radius is. So the diameter is equal to 2 times 0.056. Just to be on the safe side, we'll do this on our calculator. Clearing out the calculator, we'll take 2 times 0.056, and we find it's equal to 0.112. The diameter is equal to 0.112. In this problem, common to a machinist shop, we have easily found the diameter of the circle that will fit in an equilateral triangle with a side of 0.194. All we had to use was our basic knowledge of circles and their propositions and a little right triangle trigonometry, and that helped us to find the diameter of the circle, which is 0.112.
I'm the president and owner of Reliable EDM, where we do specialized machining, and we use a lot of trigonometry in making our parts. And this is a part of our company over here. These are some of the machines we have, and everything is done with wire. EDM is just with a thin piece of wire, and we cut the accuracies plus or minus 1/10 of a thousand, less than 1/20th the thickness of your hair. For instance, out of this bar of steel, we cut this piece. We also cut this eagle out of this piece. This is our showpiece over here. And we also cut inside, as you can see. And notice on the bottom, it's straight. And on the top here, it's curved. So we did it was made curves on the top and ended up straight. And that has to be done on a computer with programming. And we're going to go inside to our inspection room and do a problem there. This is my son Steve. He's a mechanical engineer, and he's been working for us here ever since we started 17 years ago, and he does all the difficult programming that required in our shop. And we have a shape over here. This is a flow nozzle, and it says 0.092 plus or minus 2 thousandths, and it's got TYP, which means typical. That means all 3 sides are equal. And Steve's going to do the math on this. And what we do here is, this is a flow nozzle the way we get it, with just a round hole in it. And then we put the wire in here. We thread the wire through, and by means of electrical discharge machining, we cut out the shape, and it comes like this here. This is the shape. Now, how do we know if we get 0.092 plus or minus 2? What we do is, we have these gauges here. These are plug gauges, and they're in increments of 1,000 each. And we can just go along and put it in there into the flow nozzle. That will tell us when we have our tolerances here. Like for instance, this one, 092 would be 094 or 090, which is a go and no-go gauge. And so now I'm going to turn this over to Steve, and he's going to show us the math how to do this.
Draw up this triangle. And what we're going to figure, what size pin is going to go in here. So we know that half of this side is going to be half of the 092. But we'll start out by going to the low side of the tolerance, which will be 90, so half of that's going to be 0.045. And since this is an equilateral triangle, we know that all angles are 60 degrees. So if we go to the center, we draw this triangle like this. This angle here will be 30 degrees. And so now we're going to figure out we need to find out what this height, which will be the radius of the pin, which will be the tangent of 30 degrees, is going to be equal, we'll call it the radius here, is the radius over the 0.045. Or the radius is going to be 0.045 times the tangent of 30 degrees. Grab the calculator here. 0.045 times 30 tangent. So the radius is going to be equal to 0.02598. So times 2. So the diameter of the pin is 0.0519, which we would round up to 0.052 diameter pin. And that's the low side. Now if you wanted to figure out the high side, which you would use a change this, would you go to the 94 thousandths, which would change this to the 47, and basically just take the 0.047 times 30 tangent, 0.0271 times 2 for the diameter. It's 0.0542, which will round off to the 0.054 diameter. This will be the low pin, low gauge, and this will be the high. So to have a good part here, the range of the pins will be 0.052 to 0.054. So if a 0.055 pin goes in, then we know this part's out of tolerance. And a 0.052 pin has to at least go in. So if the 0.053 goes in and the 54 is tight, then we know we've got a real good part and we're right at the middle of the tolerance. And that's how we'd figure out how to come up with that tolerance, by using a round pin.